This podcast is going to cover periodic table trends. The first trend is atomic radii. Radii is plural for radius, kind of like cacti is plural for cactus. Well, we know that the atomic model does not look exactly like it does on this screen. You don't actually have round atoms. There are p orbitals, d orbitals, f orbitals that have all different shapes. So what we have to do in order to measure the radius of the atom is to bond two identical atoms together and then measure between the two nuclei and divide it by 2. Let's look at the atomic radius and what we think the trend will be. We can predict some things here. If you look over here, when you look at each period here on the left, each period adds an energy level. When you add those energy levels, if you look at the Bohr diagram, and here's your nucleus, here's 1 energy level, 2 energy levels, 3 energy levels, 4 energy levels, and so on. So as you go down the periodic table in these periods, you're going to have an increase in atomic radius. Okay? So that makes sense. So as you go down, you're going to increase no matter which side of the periodic table you're on. However, if you go across the periodic table, that becomes a little more challenging. Let's look at the third period. So we're going to look at just this period right here and these elements. Okay? And we're going to look at that trend. Okay. If you have sodium, sodium has 11 electrons and 11 protons. And it has 3 energy levels, 3 main energy levels. But if you go all the way over to the other side, you'll notice that argon has 18 protons and electrons. Now the attraction of the protons and electrons in sodium, okay, it's got 11 protons attracted in the nucleus to 11 electrons out in the shell. That's a pretty good attraction. However, when you look at something like argon, it has 18 protons attracted to 18 electrons. Okay? When you have more protons and electrons, that attraction becomes very strong. So therefore, it pulls the atom inward so that the shells come closer. So if you have the protons inside the nucleus and you've got the electrons out here and the orbitals, those electrons are going to be attracted to the protons. And so it's going to pull the nucleus, or excuse me, pull the shells a little closer to the nucleus. So actually, as you go across the periodic table, the size of the atom gets smaller. Let's look at a diagram. Here's the diagram. So as you go down, you're increasing levels, so the atomic radius gets larger. But if you go across a period, then you actually get a little smaller because you have those attraction between the protons and the electrons in the atom. And this is what it looks like if you just look at a general trend of the atomic radius. As you go down the periods, this has the largest atomic radius because when you go across this way, you're having smaller atomic radii because of that attraction. So let's look. Sodium or rubidium. Here's sodium. Okay. And then rubidium is a little bit further down. So we're going to comparing 2 different levels. Well, naturally, rubidium is going to be larger because it has more levels. But if you look at sodium compared to sulfur, here's sodium, and sulfur is across on that same level. The sulfur is going to be smaller because of the proton-electron attraction, so sodium would actually be larger. Okay, let's look at ionization energy. First, you need to know what an ion is because the word ionization is in there. So ions are atoms that either have more or less electrons than protons. They're not neutral anymore. The energy required to take an electron away from an atom is its ionization energy. So let's look. this first group right here has one valence electron. And if I want to take that one valence electron away from that atom, he's not going to really be very upset. Because if you look, for example, at potassium, he has 19 electrons. If I took one away, he has 18 electrons, which would make him more like argon. That's pretty stable because he's a noble. So these first groups right here aren't going to be too upset if I try to take an electron, so their ionization energy is low. But as I continue to go across the periodic table and get closer and closer to the halogens, the halogen group is not going to be happy if I want to take an electron from them because they're almost at the octet. They've almost made it to be a noble. So the ionization energy, if you look at the periodic table, the ionization energy goes up as you go across the periodic table up to here. Okay, so the energy required to remove an electron goes up because these guys are not going to want to give up their 7 electrons. Okay, whereas these guys, they only have 1 valence electron, so they're okay with giving it up. Now let's look at the periods, or let's look at if we go down the families and how that ionization energy would work. Let's compare lithium to francium. Lithium has 3 electrons. If I want to take one of his 3, again, he just has the 1 valence electrons, but that's 1/3 of his electrons that I'm taking away. Compared to francium, has 87 electrons, and if I take 1 out of that 87 away, that ratio is much, much smaller. It's not going to impact francium as much. So the ionization energy is actually higher over here because there's less electrons. Let's look at a diagram. So ionization energy goes up because it's more of an impact as you get less and less electrons, and ionization increases as you go to the right because, of course, these elements are not going to want to give up their electrons, especially the nobles. So here's a trend: low ionization energy to high ionization energy. Let's look, lithium or fluorine. Here's lithium, and fluorine is over to the right. Lithium doesn't bother. He doesn't mind at all if you take away his electron. So fluorine has a much higher ionization energy because he's very close to his valence shell. Calcium is right here. Potassium is over here. Which one has higher ionization energy? Excuse me, phosphorus. Okay, phosphorus. It's much closer to having a full valence shell than calcium. Plus calcium has a full s orbital. Now let's look at barium and beryllium. Here's barium and beryllium. Barium and beryllium. Which one is going to be harder to take it away? Well, beryllium only has 4 electrons. Barium has 56 electrons. So taking one of barium's is not going to be as big of a deal. So beryllium would be harder because removing one of his 4 is much more difficult than one of 56. All right. Electron affinity is another trend. This is the energy change when an electron is added to a neutral atom. So how happy, you can think of affinity as like affection. How happy is this element going to be if it gets an extra electron? So I think of it as electron affection. Okay? So these guys over here have 1 electron. They're trying to make a full octet, so they're trying to get to 8. So these guys, they're not going to be all that excited about getting 1 more electron. They'll be a little bit excited in this column because if they get 1 more, okay, then they have a full s orbital. So it's kind of nice, but it's not that big of a deal. But if you go over to this side of the periodic table, you might notice that this column, the halogens, would be very excited to have 1 electron because if you add 1 electron, they now become a noble. So this is good. This is awesome because now they have a full valence shell. So these guys are going to be really, really happy to have that electron. So their electron affinity is high. So as you go this way, the electron affinity goes up. Okay. It's great. They're really, really happy. Their affection. And let's go down the periodic table and think about this. Are the folks up here, the elements up here that have less electrons, getting one more electron is a bigger deal to them as opposed to these down here that already have in the 80s for electrons. So the electron affinity goes up as you go up the periodic table. So let's look at a prettier diagram. Okay, again, this first group is going to be kind of happy to have an electron because they get a full s orbital, but definitely not the second group. They were happy the way they were. We're going to skip over to here. They get more and more excited about having that last another electron, especially the halogens. But don't miss out on the nobles over here. The nobles are very flat. There's almost no electron affinity. They're not happy at all to get the orbital, the electron. Just kick it out of the way. Here's another diagram. Electron affinity goes up as you get closer to the fluorine. Okay, so let's look at indium or iodine. Okay, and here one of them is number 49 and the other one is 53. They're on the same group. Iodine is going to be a lot happier to get that electron because now it'll be like a noble. If you look at germanium and carbon, okay, they're in the same period, or the same group. They're in the carbon family. And so you can look at those two on your periodic table. And definitely carbon, because now it's going to get 7 electrons where it only had 6 before. Whereas germanium's only getting the 33rd out of 32. So that's not as big of a deal. Okay, electronegativity. This is when an atom is in a compound, not all by itself. And it's how strongly an atom attracts electrons when it's in a compound. So how much force does this atom have in pulling that electron towards himself? Fluorine is the most electronegative element, and it's given a number of 4. This is just a random number for our purposes. And then all the others are less than that by comparison. So if you look at this chart, fluorine has 4. So as you go across the periodic table in periods, you have more electronegativity. And as you go down, you have less electronegativity. So fluorine is the most electronegative. You can kind of see that based on this chart. The higher column is at fluorine. Everything else is lower except for the nobles. Again, another diagram explaining the electronegativity is higher at fluorine. All right, so if you look at your periodic table, strontium or beryllium, well, beryllium, it's closer to fluorine. Phosphorus or oxygen, well, oxygen's closer to fluorine, so it's going to have a higher electronegativity. Silicon or chlorine, and chlorine, again, because it's closer to fluorine. So now you've got it. These are your trends. Good luck.